Well, I've got 5 after, so I think we should just get going and let Dave explain all the things he's going to explain to us. How many people know Dave Rowe or are aware of him? Dave's been around.
Jesse, I know.
Uh-huh. Dave Wood, you know, you've worked with, or at least worked around Dave, right?
I don't know. Do I know Dave Wood?
At one point in time in the past, we've run into each other. Yeah.
Yeah. Okay.
Well, Dave Rowe, I would say, is one of the outstanding core people in amateur astronomy, and the way this whole thing has evolved over a long period of time, and certainly has an experience base that is unique, and a really interesting job. It's really nice to talk to people that still have jobs and go to work every day. And
yeah, I wouldn't say I go to work every day, but I do have a job. I have a couple of jobs.
Yeah.
All right. Well, since we have a small-ish group, why don't we, interrupt me whenever you'd like and just ask questions as we go. I kind of like to keep it informal anyway.
Yeah, and I'll keep my eye on the chat, and if questions pop up, or just speak up. Either way, it doesn't matter.
Yeah, just shout them out if you got questions. So let me see if I can share my screen and get that going. Can you see my screen now?
Affirmative.
Yep, we got it.
I want to move it over here so that I'm actually looking at you. Kind of annoying when you're looking away, giving a presentation. Okay, so I don't know, let me try to put this in slideshow mode. Why does it do that? I don't want that. Let's leave it like this. So
looks fine on this end.
So what I'm going to talk about is kind of a potpourri of various topics, and join in the discussion if you feel like it, and certainly please ask questions. So I'll give you a brief introduction about myself, and we'll then take a look at some photos that have been done by people in the past from using Planewave telescopes. I decided I would love to talk about Planewave history and technology. You might find that interesting, an interesting diversion from regular telescope talk. It's more about the company and what innovations we put into it, and so forth over a lot of years now, more than 20 years. And I'll give you a little bit of information about the newest telescope in our line called the Delta Rho 350. It's a wide field high étendue astrograph. And I'll talk a little bit about science programs and some of the things that I'm interested in. So we'll just jump right in and get going. My background is a bit complicated. I'm sure everybody else is too, I had a little tiny department store refractor when I was, 8 or maybe 9. And I didn't even know how to use it. My father bought it for me. He didn't know how to use it either. I remember pointing it, and the stars were like this big. And I thought I was actually looking at the size of the star. It turned out that the telescope just wasn't focused correctly. And I finally figured that out. I'm not sure even how I did it, just by goofing around with the thing. But I loved that little thing, and it kept me amused for probably 5 or 6 years. And then I had one of those gorgeous Edmund 6-inch f8 reflector telescopes, Newtonian. And this is the one that I had, except it had a white tube. It didn't have the red tube. I made my first mirror. Actually, I found an unfinished mirror in the physics department. I was going to school at Bowling Green State University, And
Real, real quick, Dave, we still only see your title page.
pardon me?
We still only see your title page.
Well,
you-
that's not my fault. I think that's the fault of Zoom. So let me
Is this a PowerPoint you're showing?
Yeah.
Are you sharing a screen or an application?
Well, let me find out what I'm actually doing. I'm probably sharing the application. Let me share this. I'm sharing the screen, which is the problem. Let me share the application. Now, do you see that? You
Yeah,
see,
so there's nothing being displayed at the moment. It just says we are, David Rowe has started
Yeah.
screen sharing.
Yeah, we do see, there, now you got it.
Yep.
Just took a while to come up.
well, I'm back on to my screen number 2. So I think the problem, I would really like to talk to you directly. So let me see, let me try this one more time. That's weird. Well, let's see if I can, let's plate solve.
Oh, there's something there. Yeah.
There's some
No.
code. There's a nice star field.
But you don't see my PowerPoint.
Negative.
Okay, I guess I don't know how to do it. I guess I'll leave it over here. You'll have to look at the side of my face then. So the I was on this chart. So sorry about that. This is the little Newtonian that I had. I absolutely love that thing. And then I found a mirror in the physics department in a closet.
We're still seeing the star.
Yeah,
field.
Dave, we're still just seeing the plate solve screen.
Well, what's happening with PowerPoint? It does this from time to time. If I start the slide presentation, what do you see now?
Right now, we still see plates all.
Yeah,
My goodness, I have all screens are filled with PowerPoint. All right, let me stop sharing and try it again. Which
You
one of
did-
these things should I pick? So I've got PowerPoint slideshow. Let me try that one. Now what do you see?
Oh, it's still coming up. There you
There-
go.
now
My
you got it.
background.
now you've got my
There you go.
background, the second or third slide.
This is
Okay,
slide number
good.
4.
Super. I think we're on track now. So, all right, how come the up and down keys don't take me to the next slide? Oh my goodness, what is up with?
Okay, I've been
Yeah,
there.
there-
but You should get some arrows on the screen itself.
I got it figured out. I can use the scroll wheel to go up and down. All right,
Okay,
so finally, sorry about that. And I finished that mirror. I actually found Sky and Telescope articles, Bob Cox's monthly gleanings for ATMs. That was wonderful. So I finished I built a Foucault tester. I finished the mirror. I was an aerospace engineer out here in California for years. I could say 30 years. I did a lot of work in early GPS receivers and so forth. And I started a company with a couple of other great guys for over 20 years. And we designed integrated circuits for the internet connectivity, actually the optical fiber part of it, where you send the bits onto an optical fiber. And then kind of during that, I worked with the folks at Planewave. This was before Joe and Rick and Jason and so forth were from Celestron. They worked at Celestron. And we had a great guy at El Camino College, community college. And in the basement of the math building, we made mirrors, and we taught students actually how to make mirrors. And every Saturday and often Sundays, we'd be over there showing the students how to make mirrors. And it was a great experience for everybody. I loved it. And during that period of time, see what I have, I'll get into that a little bit later. But during that period of time, we kind of started Planewave in a sense, and kind of interesting story. So let me jump into the fun stuff. These are some great photos taken by other people. I'm not much of an astrophotographer. I loved it, but it was more of a enjoying the technology of it, understanding how to do it and so forth. So there's a beauty that came from a CDK 24. It was a CDK 17. Don Goldman, excellent astrophotographer, from a CDK 20. This is from our smallest telescope that we make currently, which is the 12.5. Beautiful images of Saturn and Jupiter. This is surprising. This is a single 60-second exposure. Isn't that an amazing? Absolutely amazing to me. If you've ever tried astrophotography, you'll know what I mean. That's you get a lot of photons from a 1 meter telescope.
That's a pretty new system in Chile, right, Dave? The
Yeah.
1 meter?
Yeah, this is a 1 meter that we have just installed in Chile. This is kind of the first light photograph, and it's performing very well. We're going to turn that into a part-time Speckle instrument, and I'll describe Speckle Interferometry a bit later. So those were all photographs taken by Planewave Instruments in the last more or less 10 years. How did we start Planewave? I don't know if all of you have heard about Planewave, but we make telescopes that are from 12.5 inches up to 1 meter in aperture diameter. And we've been at it for now quite a long time. And most people say that we are the, I would say the dominant supplier of astronomical instruments in that size range for, serious amateurs and universities. How did we get started? Well, as I was saying, we got started in the basement kind of the math building around 1996 or 7, teaching students how to make 6 or 8 inch mirrors, how to figure them, how to build the OTA, how to make a Dobsonian telescope from them, and so forth. And we would stand around, and we all love telescopes, and we would talk about what the perfect telescope was, what it meant for us, how to get it done. Technology was becoming, electronic computing technology was exploding at that time. It still is, of course, exponentially. But we knew that kind of the thing we wanted to do was to we really wanted to plop down an alt-az, because equatorials have to be aligned and so forth. My idea, and Rick kind of joined me in this, is we'd love to be able to just plop down a telescope and have it start itself up and find out where it was and go around the sky and do whatever you wanted, take photographs or whatever. And I think we actually finally got there around 2010 or 12 with PlateSolve and PointXP and a lot of other software technology and hardware stuff. And I'll show you some of the things that we did along the way. So we finally finished this. Our little group started, this is Perry, he was the leader of the group. And his dream was to have the world's biggest operational kind of Dobsonian or Altaz telescope. And at that time, we couldn't find anything bigger than a meter, which is, 39.5 inches. So we actually contracted a guy, and I'll talk about that in a bit, in 1997, I think, to make us a cellular mirror lamp. And I'll show that to you. And we talked about the design of this thing for years. Perry wanted to have an f3.3 mirror and have it be a Newtonian and have a corrector out here. And I did a little sketch of that, and I discovered that the ladder would have to be 8 or 9 feet tall to get you up there. And I knew that I don't like heights, and I knew that would prevent me from ever doing any serious observation. So I suggested we bring the focus back down here, which is where it actually is right now in this telescope. And it's called a broken focus. And that allows so you have a secondary mirror and a tertiary mirror, and the light comes out the side, and then people can use the telescope just standing on the ground. And that turned out to be a great idea. We took this around to various star parties, and we had a wonderful time with it. As I said, that's the optical configuration. There's a secondary, tertiary mirror, and what we call a focal plane corrector. I designed this for the first time around 97 or 98, and it has since become a very, very popular telescope design. It's really pretty simple. It has a spherical secondary mirror, and that's quite important to me. I don't know how many of you know Tony Hallis, but I spent a lot of time. He's kind of a famous astrophotographer in his day. And he had a Ritchie Chrétien that he could never figure out how to collimate. And I went out to his house one day, and we fooled around with it during the afternoon, not under the sky, but he had a flag about a half a mile away. There was a flagpole, and the top of the flagpole had a gold ball, and it made a very beautiful reflection that we could actually look at through the telescope. And we goofed around with that, and it's very difficult to collimate an RC because you've got to move the optical axis of the secondary mirror over or centered on the optical axis of the primary mirror. And then you've got 2 adjustments that way. You've got tip tilt of the secondary, and you've got tip tilt of the primary. And it turns out to be a job. And there are ways of doing it using software that may be easier, maybe not. We're actually working on that right now. But the fact that this has a spherical secondary mirror means that positioning it in the X and Y direction out here, in other words, decentering, has almost no effect on the optical image quality. You just got to bring the center of curvature of the secondary mirror in line with the optical axis of the primary mirror. So you got to put it on this line. And in that actually, I think, has had a subtle but major impact on the way people use our telescopes. It's quite important. It also makes the manufacturing of telescope really quite a lot easier, because in an RC, you've got to make a hyperbolic secondary mirror. And that is tough. This is a convex surface, so you've got to use like a match plate to measure it. You put it up against a surface of similar shape, and you look at the deviation by looking at Newton's rings. It's actually a piezo interferometer, a contact interferometer, some people call it. Anyway, you see Newton's rings, and that's quite a difficult task, and it leads to roughness and other difficulties. So the spherical secondary is quite an important, I think, development in telescopes. So we ordered a blank in 1997. It actually arrived like 4 years later. We put down $1,000 down payment. It only cost us $2,500 for the whole thing. It was made by Peter Wangsness in Arizona, Tucson, and he was trying to start a company based on making these Pyrex cellular mirror blanks, and we got the first one. And so here we are. This is probably 2002, 2001, I don't know. And this is how we actually ground that thing out all by hand. We didn't use a machine because Perry actually didn't want to, which, you know, in hindsight, was probably a good idea. So here we are. It came and it had this layer of about 1.5 millimeters thick that was kind of junk, foamy glass that we had to get rid of. And it took months of just grinding on this thing and grinding on it to get it down through that. And then we got the right radius of curvature, we figured it, and so forth.
I'm curious, David, what was the weight of that blank when you got it?
Right. I want to say it was 250 pounds, and it lost something like 30 pounds in the processing, or 25. So here we are again, a bunch of us. We had built, this thing is actually full of steel scrap. This barrel probably weighed 500 pounds because this mirror you could tip up for testing. It had and I think I have a photograph of that later. You can actually tip up this whole stand to test the mirror. And now here we are. We could use, 3 guys could get on this mirror and grind on it, but you had to be careful that you didn't crash into each other. So you had to turn on some like ballet music and go at it. This is Rick, Jason, Perry, there's Joe, all 20 years younger. Kind of amazing. I built a spherometer so that we could check the radius of curvature. Here we are. We had polished it out. That's me a long time ago. And 3 of us, or even 4 or 5 of us, sometimes would figure this thing. I mean, that the amount of correction this thing had, even though it's not a fully parabolized mirror, the amount of correction was measured almost in like millimeters. We had to polish the edge down. Figuring took forever. Tipping it up. We had a Foucault tester. This is kind of a joke. Jason was trying to get it to the right height, so he stacked a bunch of stuff underneath it to try to get it up. But anyway, we Foucault tested it. We did lots of other testing. We took it outside at night, and we used the 2nd floor of the math building to do radius of curvature testing that way, and so forth. Lots of interesting, fun stuff. There I am. I wrote a lot of software to analyze the test data of the mirror. Some of these programs actually still survive today. This was called Figure 4.5. So during all of that stuff, none of us really knew what we were doing with a mirror this big. It turned out I'll make a long story a lot shorter. We actually figured in 2 or 3 waves of astigmatism, which is not hard to do at all. Mirrors flex, even these large cellular blanks, they flex. So to get rid of the astigmatism, which we found by, lots and lots of complicated testing and so forth, but we found that it had between 2 and 3 waves of astigmatism. So we turned it upside down on a full-size lap, and we did what we called the big spin, which was we actually spun this whole big, heavy 250-pound mirror blank on the lap. And it slowly, over a period of months, it slowly removes the astigmatism. I mean, if I had to do it today, I would know exactly what to do, but none of us knew what we were doing. That was the fun of it. We learned a lot. Here's a spherical secondary on a match plate. So a match plate has the same figure, except it's a concave piece of glass. And then you put that on top of the secondary mirror that you're testing, and you get a fringe pattern. And there's a fringe. And there's another fringe. And by measuring the deviation of the fringe from a straight line, or actually from a section of a circle, you can determine how far you are from the correct figure. So we did all of that. This thing is huge. This secondary, I think, was 14 inches in diameter. And we finally got it to work. Many, many years later, we got it to work, and we took it around. It was March 2010. So I guess 13 years after we bought the blank. Wow, that's fancy. I don't remember putting that in there. And that led to starting Planewave. Joe and Rick and I worked up a design. And in fact, this is the design. This is the design for the CDK-20, which is where we started. And they worked at Celestron at the time, but they quit and they started Planewave 2000 and what, 4? I don't remember exactly. And I was still working in my company that I started at SMI. And we got a contract. We actually got an, or not a contract, we actually got an order from the University of Kentucky. And we supplied them with 2 CDK-20s, the first 2 production units, and they worked great after some tweaks. I mean, it wasn't all easy, to say the least, but we got it to work, and that started the company, and we just kept going from there. That's interesting. There's some sound there. Weird. Anyway, this, at the time, this was kind of unheard of. We had stars that had perfect images from corner to corner. And that's what you get with a well-corrected flat field of view, which the CDK line has. This is the 16803 chip, 52 millimeters across the diagonal. So I thought it might be fun to take you all the way to our biggest telescope, which is the Planewave 1000, PW 1000. It's also a corrected Dalkirkham. It uses direct drive motors, on-axis encoders. It's a Nasmyth focus instrument. It has 2 places where you can put instrumentation. So there's a tertiary mirror M3 down here that reflects the light down this axis. There's correctors here and correctors on the other side. And The optical layout should remind you a lot of that original 42-inch Dobsonian or Altaz, push around Altaz that we built. It's the same, exactly the same idea. Here it has 3 corrector elements instead of 2 to get a perfectly corrected field over a very large field of view. It has a 100-millimeter diameter field of view, which is 4 inches. It's enormous. And it still uses a spherical secondary mirror because it just works. Perfectly flat, perfectly corrected field, 100 millimeters in diameter. We now, instead of using our early scopes used Pyrex because that's what we could buy, borosilicate, and now they all use fused silica. It's a much, much better material. A bit more expensive, but it's a huge improvement in stability, makes figuring the mirrors much easier, testing and so forth. Here's the ray trace of the optical design. So this is the old style ray trace where you just trace rays through the telescope, and it's a perfectly good way of designing a telescope. Now, with FFTs and so forth, we can actually calculate the diffraction image of the telescope too. So this is the diffraction image. And it really is it's essentially a perfect telescope all the way to 50 millimeters off axis. We use fused silica for the corrector lenses too, for various reasons. One of them is that it's quite transparent in the infrared and in the UV, and people really like that. They don't want, people that buy this telescope would be universities and other professional organizations that image satellites and things like that. And they want to use all the photons that come into the telescope. So from 375 nanometers all the way out past 1 micron.
Dave, those the numbers of microns in that chart from 2.2, 3.7, 5 microns, is that wavelength? So are we talking about IR here?
No, this is the RMS spot diameter. It's actually the RMS
so that's
spot
the
diameter. Yeah.
Gotcha. Not wavelength.
No.
Got it.
So the optics are actually transmissive out to about 2.5 microns, or K band, as the IR astronomers like to call it. And we have people that use our telescopes. We actually gold coat the mirrors because aluminum isn't very reflective past about 1.5 or 1.6 microns. So if people that want to use it in J, H, or K band, they often order them with gold coatings, and it's quite a spectacular thing to look at a 1 meter mirror that's been gold coated. Quite nice. Okay.
A quick question for you, Dave. The differences between fused quartz and fused Pyrex, do you see a difference, or is one better than the other?
Yeah, so fused silica has about 1/5 the thermal expansion coefficient as Pyrex. Pyrex is a trade name. It's better to call it borosilicate probably, but we all know it as Pyrex. So borosilicate glass is pretty low expansion compared with plate glass, which was the original, mirror material. The 100-inch telescope on Mount Wilson and the 60-inch are both made from basically soda lime glass, plate glass. And Pyrex was a great invention of the 1930s out of Corning, and it allowed them to build the 200-inch Mount Palomar telescope But even so, and it has a coefficient of thermal expansion that's roughly 1/3 of plate glass, soda lime glass. And then fused quartz, fused silica is again 1/5 of Pyrex. So it doesn't really move at all with temperature. There are glasses called zero Dur and other glasses that are even lower, have a lower CTE, but it doesn't really make any difference. Once you're down to the very low expansion characteristics of fused silica, it no longer makes a difference.
So fused silica and fused quartz are one of the same, they're the same
Yeah.
product. Okay.
It's fused quartz. The quartz is silica, silicon dioxide. So I think the correct name would be fused silica. Many people just call it quartz. It's a quartz mirror. Quartz has a particular crystal structure, which this doesn't have. So this is more of an amorphous fused, the material has microfine grain structure. It's more like a glass than it is a crystal. Okay.
Got it. Thanks.
And Corning makes our blanks. There are other folks that make fused silica blanks, but we buy all of our blanks from Corning. And sometimes we cut them up ourselves, and other times we let Corning cut them. It all depends on what we're making and how many blanks we would like to get out of a boule. They manufacture the fused silica in 1.6 meter diameter boules and cut it up from there. They slice it and then cut it into circles and so forth. So here's a look at the OTA from the side. Same thing I was just describing. Here's the 3-element corrector. 2 other views of it. We use what we call a space fork or space frame fork construction. It's a 6-point. You've got 6 degrees of freedom to hold this thing, your axis. And so you've got to capture all 6 degrees of freedom. So there's actually 6 of these truss tubes. 2 you can't really see. There's one there and one behind it. So it takes 6 of these carbon fiber tubes to actually, these happen to be steel for a very good reason. There's no reason to use carbon fiber, and steel is much, much tougher, harder to damage. On the other hand, these are carbon fiber in the OTA to reduce the thermal expansion problem if you use steel or aluminum. Okay. There are direct drive motors and high resolution on-axis encoders in one of these. The other side is just a blank, doesn't have a motor. So why do we use direct drive motors? Well, they're compared with gears, they're incredibly nice things. Gears have backlash and periodic error and hysteresis. They have a sloppiness to them that's impossible to really get rid of. So what you do is you actually drive the axis directly with a torque motor. And I'll show you the torque motor later. And then you directly measure the position of the axis by putting a ultra high resolution encoder right on the axis. And that thing has 10 million ticks per revolution or more, typically. And then the trick is the control loop that allows you to move the telescope and keeps it positioned and stable in wind gusts and so forth. And it's very, very wonderful to use. If you move this telescope, it can slew 90 degrees and stabilize in 5 seconds, a 1 meter telescope. So you have to be careful not to be around it when it's doing that. These are usually in, remote observatories, but it will slew and stabilize and people say lock onto a target, but not really lock onto, but you know what I mean. It'll start tracking perfectly in about 5 seconds. So that's really nice. And it's great for people who want to do fast imaging, satellite. The folks that use it for imaging satellites like that. And others are doing gamma ray burster, trying to capture and photograph the light curve of a gamma ray burster, other fast transient things. So all good for that. Here's what it looks like. I won't go into very much detail. This is a complicated bugger, but it's got the axis drive coils are here, and this part of it is actually the derotator. So because it's an Altaz telescope, you've got to derotate the field if you want to take long exposure astrophotography with it. And that's what this motor's for. It's complicated. There's a lot of moving parts in this thing. I won't describe what all this does, but there's, bearings and magnets and motor and, magnetic coils and spacers and stuff. There's one that's assembled and being tested. This is roughly 20 inches in diameter, as I recall. All right, so there's another whole aspect to telescopes, and that is gravity and heat. So when you move a telescope, you're changing the direction of the gravity vector on the OTA, which means you're changing it on the mount that's holding the mirror. So what you're looking at here is actually in SolidWorks, which is a 3D modeling program. You're looking what happens to the mirror when you tip the telescope to, I think in this case, 60 degrees elevation. And then you can tell SolidWorks to exaggerate the motion by a factor of, 10,000 or 100,000 or whatever. So that's why it looks like the whole thing has become terribly decentered. Well, the motion's been magnified by some enormous factor to allow visualization of what's actually happening. So we take the output from SolidWorks. When it's in this tipped condition, SolidWorks does the calculation of the change in the surface of the mirror. And I wrote a tool to analyze that output, and it displays it graphically for you here. So this is what it looks like. And this is the wavefront error in waves at 656 nanometers. And the deflection is, the worst case deflection of that mirror is only 1/10 of a wave. It's actually about half of that because we figure that out because we actually figure the mirror on its test stand. So how do we make this beast? Well, we take a solid hunk of fused silica and we have a machine. We have like a thing that looks like a milling machine, except instead of tools that cut metal, the tools are diamond and they cut glass, or they cut the quartz, the fused silica. And so here's a blank that's actually been, it starts out as a solid chunk about 6 inches thick of fused silica. And we lightweight the living bejeebers out of it because lightweighting is super important to the telescope, both in the mechanics that hold it and move it, and in the speed at which you can remove heat from the mirror. Now, the mirror doesn't really distort because of its very low coefficient of thermal expansion, but that stored heat will heat the air in the tube and cause local seeing. So it's really nice to have a mirror that's low weight for three really important reasons. One is that one I just mentioned, it doesn't store heat for as long. And then it makes the whole telescope just a whole bunch lighter. Like the entire telescope becomes something like a factor of 5 lighter. So this telescope is 3,000 pounds, and telescopes like it are 15,000 pounds using solid 1 meter blanks. So it makes a huge difference. Here you can see the pockets. These were all ground out pockets using diamond tools of different diameters. We start with a big one and then we transition to a smaller one to make the corners. And Kevin Eyett and I worked on this design for 18 months in SolidWorks before we got it to work the way that we wanted to. So there's a lot of engineering in this thing. And there it is at we take it around now to aerospace shows and so forth, and we shine light through it. It looks quite interesting. That's Kevin.
Another question. How long does it take the machine that from the time that you put the blank down to the time that it's ready to go? How long is that machine working?
That's a great question. That's about a 40-hour exercise in machining. And we don't run it. We were going to run it 24 hours a day, right? It's all CNC controlled, but nobody felt really comfortable with that. So we only run it like 6 to 8 hours a day. So it's about a 1 week. It's on that machine for about a week if everything goes well.
And is that machine used for other mirrors for the production line of other telescopes?
Yeah, this machine is used to make other mirrors in our production line. All of them start out as flat fused silica blanks, and we machine them in various ways to make other telescopes. Not all, only the 1 meter has this complicated back to it with these pockets, but our other telescopes have conical back to lightweight and to make it stiffer under the influence of gravity. So yeah, we do a lot of mirrors with that machine. There's Kevin. So a telescope needs a control system, and that control system for an Altaz telescope is a bit more complicated than an equatorial. We've got to know how to move the telescope precisely. We want pointing to be, we want to point to any place in the sky with an accuracy of a few arc seconds, and to track for 10 minutes without having to guide at all and have, nice tight star PSFs. So there's a lot of stuff that goes into it. You got to control a bunch of hardware things, and you got to control a bunch of the operation of the telescope for observing or for taking images. And I wrote this tool a long time ago. It's called PlateSolve. PlateSolve will solve an arbitrary field of stars without any initial conditions being needed. I wrote a program called PointXP, which points the telescope. This removes the elastic deformation of the telescope to the best of its ability. So a telescope, when you move it in different places of the sky, is going to have different amounts of elastic deformation. And that changes the effective pointing direction of the telescope. So this kind of measures that. It's a kind of a calibration, if you like. So you go around the sky once and you point to different fields, you plate solve those images, and then from that information, the telescope knows how to point anywhere in the sky with, in this case, a maximum error of about 3 arc seconds, which is pretty incredible. It tracks very well. Tracking can be affected by lots of things, but in general, these telescopes track extremely well. I won't go into the details. So let's talk about what we can do with science.
Dave, it does the tracking without any guiding hardware, software too, right?
Right. So it'll take a 5 or 10 minute exposure without any guiding needed. I mean, you can put an off-axis guider on it if you want to, and you can guide for hours, and some people do. Okay, so we all know about exoplanets. It's been a really hot topic for the last, 10 years or so. There's a consortium of universities that put on top of Mount Hopkins an array of CDK 700 telescopes called Minerva. And they do radio velocity measurements. They point all 5 of the telescopes at the same object, and they actually collect all of the light from all of the telescope and put it into a single spectrograph, which I think is pretty clever. It's a way of having a 1.5 meter telescope without the price tag associated with it. We can do time series photometry, of course. Exoplanets have light curves, and you all seen the light curve dips. Well, that's a great science program for amateur astronomers who like to do science. There are organizations which will take your data and use it to calculate more accurate light curves for these objects. And it's really beautiful. Last count I remember was we now know about 5,000 planets, exoplanets. Isn't that amazing? It's only been 10 or 12 or maybe 14 years. I really don't remember it, but it hasn't been but the blink of an eye. And we now have 5,000 planets that we know about. And we got, a few examples that are getting kind of close to being Earth-like. They're in the Goldilocks zone, as they call it, the region of the orbital space, where you could have liquid water, maybe. It's still too early to tell, but every year we're getting a bit better at this. I think that's fascinating. I got interested a while back in doing double star measurements beyond the seeing limit, something that Scott is also very interested in. And we do this together using a technique called Speckle Interferometry and bispectrum analysis. This has nothing to do with the wavelength of light. It's a poorly chosen name, in my opinion, but nonetheless, it's what people call it. I wasn't quite done with this slide yet. Yeah. And then there's a whole new area that I'm quite interested in pursuing with Scott and with other people, called time series precision astrometry. That's where you measure the position of the centroid of a star on your image, and you turn it into RA and DEC with a precision that's in the milliarcsecond range. I mean, it's amazingly precise. If you do that in a time series, you can watch the motion of the photocenter of the double star moving back and forth. And this technique is particularly good at finding unusual binaries like binaries where the primary star might be a black hole or a neutron star or a white dwarf or something quite unusual, where it would be difficult to find that binary star using other methods. So I'm pursuing that. And Scott's been actually taking some measurements with his telescope for me. And I'm learning the things that are important, and everything is important, but the things that are really important. If you want to get to milli-arcsecond precision, accuracy, then you've got to do some remarkably interesting things. Oh, let's move on. Here's Minerva. I told you about the folks that put, it was a consortium originally led by Caltech. Hey, don't do that. What happened? There we go. And Minerva has these Achawan domes. There's 2 telescopes per dome and so forth, and they can point 4 or 5 telescopes all at the same object, as I said. And they bring them all together into one of these large triply ovenized $1 million spectrographs that are made by a company in New Zealand called, I can't think of their name. But anyway, they make probably the world's best calibrated spectrograph. You know, you have to, these spectrographs that measure radial velocity changes of the star that the planet is orbiting around, the Doppler shifts on the order of, 1 part in 10 to the 7th or something. It's really, really tiny. So to be able to do that, you have calibration sources, everything has to be at a constant temperature and so forth. It's an extremely difficult field. Okay, so how do you measure, hey, don't do that. I don't know, jumping by itself. So how do you measure double stars? The atmospheric seeing is typically on the surface of the Earth. It's even on mountaintops. It's going to be an arcsecond or 2. And we'd like to measure binary stars that have, say, 0.1 or 0.2 arcsecond separation. So to be able to do that, a bunch of clever folks in the 70s and 80s, mathematicians mostly, figured out how to take, you take a video sequence of images, like with, say, 50 or 100 millisecond exposure time, sometimes even shorter than that. And that freezes the seeing. So the seeing is causing lots of, wavefront distortion, and all that stuff is happening at frequencies that are, 10 hertz or 20 hertz or something like that. So you take a very short image, you freeze that seeing, and then you process 1,000 of those frames, just like a video, like a movie. And you can extract the double star information right out of it, even when the seeing would allow you to maybe resolve 2 or 3 arcsecond stars. You can actually do a factor of 10 better than that. So I wrote the program that does the mathematics behind that. And we've been using it since 2012. So here's a kind of an example of what happens. That's really weird. Okay, so this is a simulation to show you better what the process is anyway. I'm not going to go deeply into the mathematics because it's quite and not so hard, but it's, it takes a while to explain. I don't really want to do it here, but imagine you start with images that look like that. And that's really kind of what you get when you do Speckle. these images are so short that you're looking at individual photons that have arrived on the camera. So here we have, a background, and we have individual photon events. And if you average that over 1,000 images, you'd get a blob because of the scene. And if you tried to lucky stack them, you'd get something like that. And now if you use the technique called Speckle Interferometry, which basically is you take the Fourier transform of each one of these images, you calculate what's called the power spectrum for each image, and that's just the square of the Fourier transform. And then you average that for all of these images. So let's say we have 1,000 images. We average the power spectrum, and that gives you the autocorrelation. And when you clean that up, you get this, and there's the double star. Now, it's not, so this is not a photograph. This is an autocorrelation. You have to keep that in mind all the time. This autocorrelation shows the companion star in two different locations because we've lost the phase of the information in the image when we squared it to find the power spectrum. Nonetheless, some very clever guys later figured out how to put back that phase information that we lost, and you get this. So here's a, come on. All right. So here's an example that I took. Is a CDK 700, which is a 700 millimeter aperture. This one's at the Great Basin Observatory in on the border between Nevada and Utah. And here's a star that we were able to separate. Again, seeing was 2.5 arc seconds that night, and here the separation is less than 0.4 arc seconds. And this is very useful information. We learned a lot about the universe from studying binary stars. As they orbit each other, you learn about their masses, and you can determine their spectral types. So you can tell this one they might be two main sequence stars, or one might be a red dwarf or whatever. And there's a lot of just basic information about the universe that we've acquired by studying double stars. So the program, has an ability to measure all the stuff. So recently, we've had a lot of interest in wide field instruments. Astrophotographers love this, but also the folks that do sky surveys of various types. They're looking for lots of transient behavior or whatever, or they're measuring they're doing photometry, looking for unusual things. They want wide field instruments. So I designed this about 3 years ago, and we're bringing it into production. It's this is a 14-inch or 350 millimeter aperture f3 telescope that covers a 70 millimeter diameter field of view. So you can put an enormous CMOS camera on the back of this and have great images across the entire field of view. The image circle is greater than 3 degrees. The optical layout, the spot diagram, and so forth. And one of our first test images. And that's the end of the talk. I hope you enjoyed it. And let's see if we have any questions at the end of this.
All right, so there was in the past, how did Celestron play into the creation of your company? I had heard that Celestron decided they want to get into the business of trying to make big giant mirrors, and it didn't play out well. And part of the result of that is that Planewave was formed because of that inability to create those large telescopes. And in the process, the SDAA and the Orange County Club got the remnants of some big blanks that we turned into telescopes for our club.
Cool. Well, yeah. So you got it about right. I'm trying to think, probably around the year 2000, Celestron decided that they wanted to have a large telescope, or even a series of larger telescopes. At that point, they made most of their money probably from the C8 and the C11. And then they made the C14, of course, but they didn't sell very many of those. And they made a few 16-inch SCTs that were scattered around in observatories, but I would say probably, 5 or 6 or something total. And they wanted to, they were competing heavily with Meade, and they wanted to, Meade was trying to develop at that time some ungodly thing like a 20-inch SCT, which is almost an impossibility. That's a Schmidt corrector plate that's 20 inches in diameter is just impossible, in my opinion. And I've tried them up to, I've tried them in my own personal shop up to 14 inches by various methods. So they were competing, and they wanted a large telescope, and they had seen my work, and they wanted to build a corrected Dalkirkham, a CDK telescope. So they carved out a piece of territory in their laboratory, in their optics shop and so forth, where they attempted to make a CDK 20. And they were actually pretty much, in my opinion, on track. I was consulting with them to help them in this endeavor from time to time. I wasn't deeply involved. The trouble was that Celestron was in litigation with Meade at the time. You probably remember that. It was about, driving telescopes with motors and a bunch of complicated stuff. And then Celestron was purchased by a Chinese company, and Rick and Joe still had the huge desire to build these larger telescopes. So they got some funding, they got some help from Celestron. It was a very amicable separation, and they went off and they tried to do it. And as I said, we had a contract from Kentucky and a couple of other places, and they pulled it off.
Cool. I heard something along that line. It wasn't clear to me how that relationship. I knew it was. My understanding was it was an amicable thing. Like, yeah, we tried this. It's not really in our ball game. We've got some other things going on here. You guys have that and go have some fun kind of stuff. So that's what I'd heard.
Right. The Chinese company that bought Celestron was really interested in moving the optical fabrication to China. And that was really all they wanted to do. They didn't want, at that point, innovation. Okay, anybody else?
Dave, the Delta Row 350 is kind of where Planewave is now, with a small wide field instrument. The history of that, how does that fit in with RASA and Celestron and all that stuff?
So I as you probably know, designed the RASA telescope along with Mark Ackerman. The way that happened was I consulted a lot with Celestron. I developed software for them to do their Star Sense technology, which is, this automatic plate solving and pointing a telescope accurately, so forth. And I knew the guy, I knew the engineering team really well. And I was sitting in there in Corey's office at the time. He's now the president. He was the chief engineer at the time. And I said, Celestron, I would love it if Celestron made an astro camera, like the old Schmidt. I had built Schmidt astrograph, and you have the curved focal surface, the film goes over this curved focal. It's just a nightmare to focus. It's an absolutely horrible instrument to use. You have to be totally dedicated to do astrophotography with a Schmidt camera and film. So I said, I've fooled around with designs for many years now, and I know how to correct that curved focal surface. Why doesn't Celestron build a Schmidt astrograph for CCD cameras? And we discussed that for months. I mean, we kicked it around, and I finally came in we talked about putting the camera inside of the OTA, but that's a horror. You don't want to put your camera inside of the OTA, where the original Schmidt camera, the film goes inside of the OTA. The Schmidt corrector is way out here and so forth. So I moved the focal plane outside of the optical tube in front of it and came up with a design and showed it to them. And we talked about it, and they didn't like it because they had to make a new corrector. And everybody realized that that was a really bad idea. To make these correctors for Schmidt Cassegrain telescopes is a very serious job. They first have to make a pull down plate called a block. And you pull the glass down onto the block into the precise figure that you want that side to be. Then you grind and polish the other side and so forth. These blocks are like the crown jewels of the company, right? So they weren't going to make a new block. So a few months later, I walked back in with the idea, well, why don't we use the corrector for the C11, and I'll just change the primary mirror to make it work optically. So that's really what we did. And I sent them a bunch of designs, and I didn't hear back from them for a long period of time. And like a year, I walked back in for some other reason, and on the bench was a telescope of my design. They showed it to me, and they said, look, we took your idea. We sent it to a professional optician guy named Mark Ackerman. He turned your 3-element corrector into a 4-element corrector and made it a little bit better optically. And we're going to call it the Rowe Ackerman Schmidt astrograph. And it started out as an 11. It's a C11 corrector plate with a different primary and with the corrector in front. And that's how it started.
But now you can also take and just put a different, I guess it's the same corrector plate, but you could, on just a C11, can't you put a camera in front of it? And
there's two things one's called the Fast Star and one's called the Hyper Star.
Yeah.
And those are correctors, but they, since they're not integrated into the optics themselves, the correction is not very good, frankly. I mean, I don't want to knock the Hyperstar because it's kind of a nice piece of gear, but it's not at all optimum. So it doesn't give you great stars, except more or less in the center of the field of view.
Zahir, you have a question?
Anybody else?
Yeah, in the chat window,
Oh, sorry. Oh,
from Zahir Wala Muhammad, are any of these scopes modified or designed with adaptive optics? And what would it what would it buy you with these telescopes designs?
Yeah, very common question. I get that a lot. It's a great question. So there's two types or several types of ways of actively correcting what the atmosphere is doing. The atmosphere affects the starlight in every possible way. So it causes some amount of defocus, some amount of tip and tilt, which is motion across the image, and some amount of spherical aberration and astigmatism and some amount of coma. In other words, you get the idea. There's this whole progression of different things that the atmosphere does to the image. And we'd like to get rid of as much as we can, given the amount of starlight we have and the amount of money we have, and so forth. So it's fairly straightforward to get rid of tip and tilt. If you have a piece of glass and you can move it in the X direction on a gimbal or in the Y direction like this, tip it in the gimbal, that will shift the image a tiny amount on the image plane. So if you can measure the amount that star has moved from where you wanted it to be, then you can use this tip and tilt plate to get it back to where you wanted it to be. And that's what we call active optics. That, people like SBIG made a AO7, which was a tip tilt mirror, and then they went that's a mirror that's wobbled back and forth. But then they went to a glass plate that it tip tilt. Okay, so that's just tip tilt correction. And that's roughly 25 or 30% of what the atmosphere does is tip tilt distortion. The next big one is defocus. And defocus is a real problem because to measure defocus, you don't just measure the position of the star. You have to, it's complicated, but you've got to have a vibrating membrane or some way to dither the focus to tell which way to go to make it better. And then the next one is probably astigmatism or coma, I don't know. Anyway, you get the idea. As you get past just plain old tip and tilt, you're into the realm that they call active or adaptive, optics. And adaptive optics generally requires a wavefront sensor. In other words, you have to measure the distortion of the wavefront as it comes in or propagates through the telescope. And then you have to have a deformable mirror so that the light that came into the telescope bounces off a little mirror that often only like an inch in diameter or so, that is a thin membrane that can be distorted to correct for the aberration that the atmosphere caused in the wavefront. So the light comes through the atmosphere, it gets kind of distorted some way. And now your deformable mirror removes that distortion as best it can. So that all sounds straightforward, and it's relatively straightforward. The trouble is you've got to do it fast because the atmosphere is changing, between 10 and 50 hertz or even 100 hertz. In other words, you've got to do it every few milliseconds. And to be able to do it every few milliseconds, you've got to measure the wavefront distortion. every few milliseconds, which means you don't have very many photons. And so you can only do it on bright stars. And that leads people to shine, 40-watt sodium lasers into the atmosphere to get enough light backscattered through the atmosphere to measure the wavefront distortion. So if
No,
you see,
Palomar would never do that, would they? Palomar wouldn't do that.
well, they do it at Palomar. But they have to get permission from the FAA before they do it. And they have to get clearance from a couple of Air Force bases and so forth. So it's not a simple thing. They've got to tell everybody that they've got a laser, because you can blind a pilot or disable some of the sensors on an aircraft if you run through a 40-watt sodium laser. So
Yeah, hey, Ken?
Yeah,
Is Palomar still doing the artificial guide stars, or is that?
No, Palomar
just-
hasn't done that. When they went to the Palm 3000, they did away with the laser for all the reasons you said. Palomar even had, if you looked at the blacktop up there, you notice some white X's drawn. They were required to have staff members with binoculars at those X's looking up at the sky where the laser would be pointing to verify, human verification, that they weren't going to laze an aircraft. So they have done away with that for a long time. And then the Reed Riddle, you had his name up on one of the slides, came up with this UV adaptive optic system that doesn't interfere with pilots. And that was advertised as the way that medium-sized telescopes could use an active a laser system on a fully automated telescope. So in other words, you didn't have to plan your spot and get clearance and all those things. You could laze wherever you wanted.
yeah. So when he's talking about a medium-sized telescope, he's talking about like 2 meters to 4 meters. That's what astronomers call medium-sized.
Yeah, that's right. He tested it on the 60-inch.
He did, and he actually moved that whole system to the 2.1 meter in Kitt Peak.
Right.
And he's doing that there now, I think. And they have laser adaptive optics on Mauna Kea and various other places around the world. But it's so it's not, amateur level stuff we're talking about. You can do adaptive optics for a dedicated person could probably do it for under $10,000 now. You need a Shack-Hartman wavefront sensor, you need a computer, you need a deformable mirror, and you got to figure out how to drive it and so forth. And, you need some beam splitters and other stuff. But again, the problem is the lack of photons. You can only do it for very bright stars, and they're not particularly interesting because they've been studied to death already.
Yeah, I think Palomar advertises that they can get good AO correction down to magnitude 17, which is good, which is pretty good. But I think from what I've seen, they tend to limit it to about magnitude 14. A natural guide star.
With a 200-inch mirror.
200-inch mirror, yeah.
Yeah, so a 20-inch mirror would be a factor of 100, so the 5 magnitudes, so you're talking about, 8 or 9th mag stars, which is about what you can do with a 20-inch telescope.
David, at one point in time, I thought I saw an RC in the Planewave catalog. Did you guys make a 17-inch RC for a while?
We actually make RCs sort of semi-custom order. We don't like to take kind of random orders from companies. We like to do off-the-shelf stuff because as soon as you get into the fully custom design and fabrication, you're into, you know, you go up probably an order of magnitude in cost. So, but we will take our CDK 17, we've done that quite a bit, and we will turn it into an RC. So we remove the corrector and we refigure the mirrors. And to give you an example of how expensive that actually is, we send the secondary mirror, which is this strong hyperboloid shape. We actually send it to an optics company that specializes in doing that. And I probably shouldn't talk about prices, but it's at least a factor of 10, maybe more than a factor of 10 more expensive than building a spherical secondary in our shop. So it's a very expensive thing.
Yeah, if you look right there over my shoulder, and that telescope, that's actually a Paul Jones deep sky instrument 14.5 RC with the quartz substrates in it. The gentleman who donated that to the club wrote the fat check for it, and so for a 14.5 inch telescope, the check he wrote for the OTA was $22,000.
Yeah, so you get the idea.
Oh yeah,
Planewave was really, our success story is really the CDK success story. That optical design is very nice for all the reasons I mentioned, and I really think it had a lot to do with the success so far of Planewave. And we don't deviate very far from that, but there are certain customers who, you know, you stand up and take notice when they want to buy your telescope, primarily NASA. You know, NASA bought 2 RC 700s from us recently to do laser comm to the moon. And when NASA calls, you know, it's hard to say we don't do that.
right. They have a very big fat checkbook, you know.
And they got a very, very good deal on those 2 telescopes. So the only add-on that we put to make it an RC was we added on the cost of purchasing the hyperbolic secondary from another company, which is expensive.
Yep.
Planewave just installed the 1 meter telescope up at Palomar in that small observatory that used to house the 24-inch scope. And there's a story behind the 24-inch. They offered it to SDAA and TVA, and we're all in there looking at it and thinking, my goodness, what is this? And, you know, if we wanted a telescope this size, we'd just buy a Planewave. We wouldn't try to get that thing to work.
Yeah, getting old telescopes to work is another whole, you know, job. I would send you to Dan Gray at SciTech if you wanted to.
Yeah, but plus it was heavy. But did you go up for the installation? They put something up on YouTube about the install, which was kind of neat. And the impression they gave probably took a couple of days to get it all assembled and craned in that little observatory, which was really impressive from a size standpoint, because that really isn't a big observatory. But I got the impression after the couple of days, they tested it out with an eyepiece and it worked fine.
Yeah, I was actually not in the country. I was in Colombia during the install. But, you know, one of the things that we have made sure that we always do well is installs. Customer service is a big part of the business. And there's been many, many telescope companies that couldn't get it done. You know, they install a telescope and it kind of never works, and they goof around with it for 6 months or a year, and then somebody else takes it over, and on and on. You know, you hear in my business, you hear these stories all over the world. So one thing we've concentrated on is our telescopes are completely functional in the factory and have passed star tests under the stars and so forth. We disassemble them we box them up. We have toolkits and accessory packages and stuff that go with the telescope. And if we don't get a 1 meter running the first night, then we feel a little bit disappointed, and it always runs the second night. So, when you do that for customers, you get a lot of repeat business.
Yeah. You should have a word or two with Vito, huh, Dave?
Yeah, I'm not sure that Vito would listen to anybody, but Vito at PureTech making the theoretically pre-made observatories, not so pre-made.
Well, yeah, we most of the time we end up having to fix the driver for the dome because it's not working correctly.
Yeah.
And it's not even our responsibility. We don't sell domes. So the dome is supposed to be set up and working. And often that's the thing that prevents us from using the telescope the first night, is the dome doesn't work for whatever reason.
Gotta be other questions out there.
Yeah. Anybody else got a question? Just pipe right up. I hate to, we could keep Dave going until 11 o'clock, but
Yeah.
probably wear him out.
maybe why don't we leave it with one of these spectacular astrophotos that people take? I love these things. I mean, I don't know how you do that. I never learned the art of astrophotography, processing something like that. That's absolutely gorgeous in my opinion.
Yeah, well, many of us in this group spend a lot of time with PixInsight and other codes doing just that. And it'd be a lot of fun to see how the individual photographers that took these, what they did to get to the finished product, because it's a real challenge and an art, and
it's a beauty.
A lot of fun.
Look at the halo. You can see, the halo of stuff around this galaxy. It's really a gorgeous image, in my opinion.
Yeah, that's nice. That's nice for a 24-inch scope. Very nice.
Okay,
Size
guys.
matters.
Well,
Size matters.
size does matter.
Yeah.
Always, right?
And time matters too. You can buy some size back with time, but
Time matters.
there's a limit to that.
Well, it's been a real pleasure talking to you. Thanks for the invitation. Scott and I work together all the time. If you have any interest in doing a little more science, pursuing something like that, then join us.
Yeah. Yeah, well, it's just great having you talk, Dave. And
thanks a lot.
Certainly, we all appreciate it. I was a little surprised the audience. We had about 16 in the end or so, and normally we have a few more than that, sometimes less, but
it's not a problem at all. I'm totally psyched to give a talk.
Quick question, David. Are you familiar with a guy by the name of John Downing?
Yeah, I know John Downing. Only from email, exchanges.
Sometimes that's pretty lucky, because if you know him on a telephone, you'll spend a whole lot of time in class with Scott.
Okay.
But I know John's been doing quite a bit of work. I think he's got an L600 and a 17.5 at SRO. Yeah, and I know he's going to put another one. I think that he's working with you guys on putting up an observatory in Chile, as I've been heard. At least he's telling me that's what he's doing. So
yeah, and he has great interest in the Delta Rho 350 and so forth. Yeah.
Does he really?
Yeah.
Yeah, he's about ready to donate. He's got an
remember he had those couple of RASs, didn't he? That he.
Oh yeah. Actually, we now have the RASs.
Yeah.
We as a matter of fact, we're still trying to figure out how to use the RASs with CMOS cameras in our public outreach. We figure that those are fast enough that you could put a nice CMOS camera on the front and get very quick quality images out of that, and be able to do. And we've got a couple of members in the club that are very active on as far as doing live YouTube type things with on public outreach, where they'll get on and they'll do they'll take image sessions. And right now they're using a really old C8, but we're trying to take one of those 11-inch Razas. It was a series 1, I think, that John had. He donated 2 of those, and we're seeing how we might be able to utilize the 11s to do public outreach, as far as being able to do something live, a public outreach live event.
Yeah, it's great. I've seen live stacking demonstration.
Yeah, that's exactly
Using
what. Yep.
yeah,
Mhm.
in a minute you can get quite acceptable color images from
Oh, yeah, no.
color CMOS camera. It's
Yeah,
quite
Yeah.
wonderful.
Gary Hawkins and Dave Decker from our club have been very, very active in doing just exactly that. We've got they've got over 70,000 YouTube followers when they start doing things. And I can't remember time, and I can't remember what they're doing now, but the next thing they're going to be doing is a partial lunar eclipse using that same technology. So it's pretty slick. Well, that's kind of one of the plans we've got to use for the Razas. I know John had kind of using them remote, trying to focus them remotely is kind of you never could get that quite right. So he took them off, and I believe he now has a 12.5-inch CDK in the observatory at TDS that he's about ready to donate to the club. So
Yeah, he's got the observatories galore. I mean,
oh yeah,
there's the ones at SRO in South America, plus the one in at our facility is he spent so much time on it. It was like a couple of years developing the thing, and I think he's much more interested in developing new telescopes than he is in using them.
yeah, I think it's probably the case.
like me, right?
Yeah.
I love telescopes, and I like to use them once, and I like to move on to another telescope.
I
Yeah,
think
well,
John's definitely project oriented. Let's put it that way.
Yeah, for sure. But,
Yeah,
but
well,
we will be the benefit of some of that. So
Yeah.
that's great.
to each his own.
Yeah. Well, Dave, thanks a lot. We really appreciate
yeah.
it. And I guess I'll see you in the morning, right?
Yeah, great meeting y'all. I really enjoyed it. So
Hey, real quick, Scott, you had asked about using tarot. Is
Oh,
using
yeah.
tarot-
Right. I think, Dave, you and I talked about it. Tarot is 12.5 inches. It's a RC.
It's a 14 and a
I'm
half.
sorry, 14.5 inches, not 12.5.
That one right there.
And the plate scale is about 0.7.
mhm.
So that's a little bigger than perhaps you'd like for the photo center work, but it'd be very interesting to see how well that plate scale would work. And I'm gonna Dave and I and the tarot people will plan to take some images and process them through your software and evaluate how we can do with photo centers.
Yeah, let's do an observing run and find out what we face with such a large, pixel scale or
Yeah, right.
low magnification.
Large. It's really, really small. No.
Well, yeah, we work in my telescope in Chile. The telescope I have in Chile, the 24, I work at an image scale of 0.2 arc seconds per pixel.
Yeah, and the speckle scale
And
should be maybe even smaller than that.
Another factor of 4. Yeah.
Tiny stuff.
But we're not gonna mess with the tarot configuration. I think that's off the table unless somebody has a lot of money and a big motivator of some kind. It's
We might maybe do something with John's observatory if we get that close with it. But
yeah,
Tarot's kind of fixed. It's a 14 and a half with a 16803 camera on the back of it and 10 position filter wheel. It does pretty good it does good exo work. Scott sends up the programs for the exoplanet stuff, and I occasionally point it at, pretty objects and go take pictures. So,
Yeah,
Mhm.
yeah, the pictures are beautiful. And some of them are extremely deep. I mean, Dave goes for, what would you say, days and days and days?
40 hours.
Yeah,
So I'll probably put between 35 and 40 hours on a lot of projects, especially those that involve narrowband.
yeah, they're very impressive pictures.
Yeah, you
So-
need a lot of photons.
Yes. All
Okay,
right.
guys. Well,
All right.
great meeting, and thanks a lot, Dave. And
You're very welcome. And
Yeah,
Appreciate
Dave,
it.
thanks a lot. Great talk.
Yeah, thank you.
I'll
for
see
sure.
you, Scott, I'll see you tomorrow morning, huh?
yep, 10 o'clock,
All right.
right? Okay.
Yep, 10 o'clock.
All right. Good night, everybody.
Good
All right.
night.
Thanks a
Thanks,
lot. Bye.
guys.